In the last video, we ended up with this 2x2 matrix that was the essential energies of the hydrogen molecule. And we said, without explaining much, that that can reduce to a qubit. So a qubit can handle all the information for a hydrogen molecule. Now remember, it's a quantum bit, not a regular bit. A regular bit would just be 1 and 0, and that's all we could come up with. Well, let's start with the 0 and the 1 and say that 0 is defined as the bonding orbital, or the bonding Slater determinant, and 1 is the anti-bonding. Now, does the hydrogen quickly jump from one state to the other? In other words, it's either all bonding, and it's at that ground state, and everything's cool, or does it immediately split into two atoms that are anti-bonding? No, most of the time it's somewhere in between here. So how do we represent that somewhere in between here? Well, when we talked about the hydrogen atom, we said that these Slater determinants, or these determinants, would have to actually superposition of determinants to describe all the factors that are involved. So if I define 0 as the ground state and 1 as the anti-bonding state, then somehow this qubit can represent a whole bunch of superpositions in between here. Just like this represents superpositions between here. And remember, these B are the mixing states. It's not too clear yet, but I'm just going to keep pushing on so that we can find out something. In the second quantized Hamiltonian, we showed that there are creation operators and annihilation operators. And instead of those kinds of operators that maintain the anti-symmetry properties that have to occur, we have these things called Pauli operators. And I'm just going to go ahead and bludgeon my way through here and just say, here are the operators. There's actually 4 of them. The I stands for identity. The identity operator, just when it operates on a 0, and the 0 vector we can think of as a 1, 0, and the 1 vector being a 0, 1. So again, I'm just going to keep moving through this, and hopefully it'll all start fitting together. But notice that the identity doesn't change anything about the state. The Z vector or the Z operator will, when it operates on a 1, it makes it a negative 1. When it operates on a 0, it just gives 0 back. The X operator, which is this guy over here, will invert the 2 so that it just swaps the 2 around. 0 goes to 1 and 1 goes to 0. Then there's this animal called a Y operator, and you'll notice we've got these imaginary constants here, and those relate to phase shifting. Now for the hydrogen molecule, there's no phase shift that's going to occur. Other molecules will see that the phase shift does have an effect on what's going on, but this doesn't have any effect unless it happens to be in a magnetic field, and then the phase shift would start to show up. Here's what happens. The Y operator applied to the 0 gives us a I, and a Y to the 1 gives us a minus I. And again, if you want to do the matrix calculations, you can use these formations or these representations of the 0 and the 1 times these matrices to come up with the results that are shown here. Now, where are we going next? Hold on to this information and we'll start applying it, and maybe you'll get the idea as we go along here. But coming back to this superposition thing, the qubit can have superpositions between this 0 and this 1. So it really defines an infinite number of conditions, just like the 2 by 2 matrix here describes an infinite number of superpositions between the bonding and the anti-bonding state. Let's start with this determinant again. And I'm going to emphasize that that determinant represents the Hamiltonian. The Hamiltonian for this element, it acts on the ground state on either side of the Hamiltonian. This state, it acts on the anti-bonding state on either side. And the mixing state is represented as this expression. Now, how do we convert this stuff into the Pauli structure? That's what this represents over here. It's coefficient A times the invert operator. I'm sorry, not the invert. The coefficient A times the identity operator. The coefficient B times the Z, or if you remember, that caused a sign change on 1, and coefficient C for the swap operator. So let's see how these things work. Well, let's start with the simplest one, as far as I can see, is the C we plug in here because this is where the swap is going to occur. If we look at the A, this is not so easy, but let's concentrate on the B first and notice that the B has two different signs. So the Z operator represents this sign change between these expressions. And the A operator, which is left over, that's the mean energy. So let's now look at how those relate. Well, A plus B equals E00 or EGG, and A minus B equals E sub 11, which is EUU. Solving for A, we add these two equations together and we get 2A equals E00 plus E11. If we divide both sides by 2, that's what we get for A. B is, if we multiply the bottom times -1 and add these two equations together, we'll get 2B, and then that makes B equal to E00 over 2. So hold those ideas in your mind. A represents the mean energy. B, which is the Z operator, represents the energy difference. And C equals the mixed configurations, this thing up here. So A does not affect dynamics. Not sure why I wrote that in there, but let's just hold on to that thought. B are orbital energies and Coulomb attraction. Okay, these are the first part of the Hamiltonian, and C is the electron-electron repulsion. Now, to close all this off, I want to bring out these two animals from the second quantized Hamiltonian. Those represent wedge product operators that ensure anti-symmetry. If we have qubit versions, what is the Pauli operator version? This ugly thing are the two Jordan-Wigner transformations. And I'll just point out a few things. I'll start over here with this strange symbol, which is, rather than a summation, that is a product of all the z's that are less than j. And really what it does is it counts electrons to the left. Wow, what a great picture! Now what in the heck is this all about? Here's the states that we're used to looking at, 1100 and 0011. And guess what? These are the mixing states. So it's really a 4-state Hilbert space. How in the heck did we ever get this down to 1 qubit? Well, that's what's shown down here, is that 1100 can be captured by 2 qubits, 00, and 11. So there's your 2 qubits. But by symmetry and at short bond equilibrium, these are the only 2 that show up. We don't see the 0, 1, and 1, 0 because of symmetry and because of entanglement. What we have been talking about is 1 effective qubit, but 1 qubit's really not going to cover the situation that handles all 4 of these states, including the mixed states. It might be helpful if you pause the video and read all the text that goes along with these different items. But what I really want to do, and I hope that's what you want to do, is use the quantum computer. So I think we've laid the groundwork with everything we need to start looking at the quantum computer code. I can't wait to see you in the next video.